Welcome everyone to the spring seminar series of the Oxford University Polar Forum. Today, as many of you already know her, I will introduce her anyway. We're very pleased to have Professor Mary Edwards with us to talk about Thermokarst lakes and wildfires, amongst other things. And a short introduction before I basically leave the ground to Mary. Mary is Professor of Physical Geography at the University of Southampton, but also adjunct faculty at the University of Alaska Fairbanks. She is the UK representative to the terrestrial working group of the International Arctic Science Committee, and has quite a long career made working in the north, especially in the areas of Thuringia, both sides of the Bering Strait, and is interested in environmental change with a focus on vegetation, I would say, and across quite a wide range of spatial and temporal scales. Many times working on with paleoecological material. Recently, she has been involved in starting a UK-Russia research group focused on research in the Far East of Siberia and of Russia. And that's it. I think there is no need for extending further into the introduction. Just thanking you very much for being here, and looking forward to listen to your seminar. Let's see if you share the screen and everything works as when we tested it.
Yes, and that my computer is plugged in.
Yes.
Right. Let's try this. Okay. Let's get rid of some of this stuff here. Can everybody see that? And can you hear me okay?
Yes.
Excellent. Well, I will begin. I couldn't resist calling it a story of ice and fire because it gets close to almost being a joke. But nevertheless, this has become a very interesting topic for me, and hopefully I can explain why. There's a long list of collaborators here. This is a story about work that has been done and some that is happening now, and a bit about what actually we hope to do in the future. So my collaborators, the first group are for work in Siberia, the second group work in Alaska, and Martin is my colleague in the DEMA project. So what am I going to talk about? Very briefly, to set the scene with Arctic change. I think you are all familiar with this, but I'll place it in a context anyway. And then I will introduce Thor Lakes in a very qualitative fashion with no intense thermodynamics or anything like that. And then look a little bit at why Thor Lakes have probably become famous, which is their production of methane. But again, just briefly and in a qualitative sense. And then I want to move on to its connections with climate change, with fire, and how it is affecting people. And hopefully that will leave me time. We'll end in Siberia, and that will leave me time to talk for a short while about our DEMA network. So obviously the Arctic is changing. Amplification of Arctic climate change means it's changing in a rapid way and in a major way, which of course affects everything, because the Arctic has a lot of people and communities within it and on its borders, and both the biophysical and the human are intertwined. And this is because of anthropogenic global warming. And as we read or in our own work consider or hear from the media, the idea of tipping points where things change somewhat abruptly from one state to another and have major repercussions on the system, is something that we're particularly worried about in the Arctic. And the state of terrestrial permafrost on the ground affects carbon budgets, hydrology, and people's lifeways. And below here, we see a picture of a Thermokarst slump where ice in the ground has melted and the material has flowed away here into a river. The top one is the most often perhaps presented concern about the Arctic, which is a tipping point where the ice becomes so thin and discontinuous on the Arctic Ocean that it stops reflecting light and heat, and instead water starts absorbing it, and we suddenly move to a non-ice situation. So all of these things are worries about the Arctic. And permafrost, then perennially frozen ground, the invisible part of Earth's cryosphere. And we can see from this map, everything blue is land affected at least to some extent by permafrost, under the surface, under a shallow active layer which thaws in the summer season. We have perennially frozen ground or permafrost. Very often this contains massive ice, often in the form of ice wedges. And this is where the issue is, because this ice can melt and then many things change in the environment. This photo by Chris Arp shows very nicely the fairly shallow wedges here on the Arctic coast of Alaska being eroded very rapidly by a relatively warm ocean and leading to rapid land retreat. So I want to talk particularly about Thor Lakes, and Thor Lakes have been known to both Russian and North American scientists for a long while. And my mentor early in my career was David Hopkins, who was a geologist and much more, who worked in Alaska and wrote a very early paper in 1949 about his observations on Thor Lakes and Thor sinks, as he called them. So the ground contains large quantities of ice, which in volume greatly exceed the natural porosity of the unfrozen material. This is excess ice. This means the ground is stuffed with water. And when that ice melts, the water either accumulates in a depression to form a lake, or it flows away and leaves a hole in the ground. And interestingly, even back in 1949, Dave was concerned about whether under the present climate conditions, this permafrost was stable. So just to explain how this happens with some visuals, if we think of these ice wedges as we saw in Chris Arp's photo, just under the surface of the ground, here's the active layer. And we maybe disturb the ground and let more radiation in, or we put a shallow pond of water from snowmelt in the summer. Both of these things add extra heat into the ground and begin some kind of melting process from the top. And in the end, the thing melts down far enough that maybe the water and the sediment slump into this hole, forming a lake, and we'll see a lot of these later, or maybe they flow away, as in that photograph I showed, where the ground was slumping away into the sea. In either case, water and sediment are dislodged, dislocated, end up in a different configuration, and we lose ice from the ground. So if we just look from the air at some Thermokarst landscapes, at the same volume of geological Journal of Geology that Dave wrote about the Seward Peninsula, Bob Black wrote about the Arctic coastal plain of Alaska. And what was fascinating were these oriented lakes that all have a very, very clear orientation to them. In fact, he said he thought they had a polygenetic origin, that they formed probably in various ways. But what is clear is many of these are shallow lakes that are formed because the ice wedges underneath them have melted. And some of the things we can observe are along the tracks of streams, there are fewer of these large lakes because streams actually capture lakes. And we see a lot of small ones amongst the large ones. And here's a rather nice iconos image that shows some of these lakes in more detail in a slightly different piece of terrain. Lakes form in the ways that I have suggested, but then they have a life of their own. They may tap into or be tapped into by a stream that may allow them to drain, or in fact to become fuller. And so here we see a couple of basins which have emptied, a couple of basins which are full, new lakes forming as permafrost further degrades in this old lake basin. And we'll see more of these patterned ground appearances. This is the pattern of the ice wedges that form a network under the ground, revealed as the vegetation is stripped away, and in this case, the lake bed is revealed. So drainage can also be by down cutting via a line of ice wedges, which is a point of weakness in the frozen ground. Here's a slightly different landscape in Alaska. These are uplands covered in thick loess, which was deposited during the glacial period. And into this thick loess are deep ice wedges. And I will look at them more when we get to Siberia, which is a place where these are really huge ice systems in the ground, in Yakutia, for example. So this is the southern marginal upland of the Yukon Flats. This is the Yukon Flats Basin in northeast Alaska. And again, we see lakes kind of embedded in this upland rolling landscape. And it's hard to see through the trees as to what is going on. And in fact, there's an extraordinarily dynamic movement of the geomorphological surface underneath these lakes. We can see here lakes as shown, some lying in valley systems, some embedded on high ground, some which have done a drainage thing and drained away, but also the land itself. It sort of looks like one of those puddles that's drying out and starts to have sort of crinkles in it as the mud dries. These are movements, and these features are 5 to 10 meters tall or taller and hundreds of meters long. And it's if this whole landscape were gradually sliding and sloughing downwards. And our thought about this is that it's probably largely an ancient feature. One of the reasons for that is that some of these lakes cut through these features or corrugations of kind of slipping material. We know that many of these lakes are thousands of years old, in fact, dating probably to the early Holocene. And also the trees growing on this landscape do not tip over. Thus, this is not an ongoing process in any noticeable way. But what it means is this landscape was hugely dynamic, probably since about 10 or 11,000 years ago. And while these processes have probably slowed down, possibly because of the covering of a now dense insulating forest, they're still probably active. Here's the evidence that's from one of those lakes that suggests its formation occurred about 12 or so thousand years ago, with the onset of the Holocene and warming of the landscape. And in these sediments, there's a lot of charcoal, suggesting the landscape burned. And it's a mixture of mineral material, the loess, and of organic material. So it's called a trash layer. And it basically is the bottom layer onto which everything else collapses. And as the hole in the ground deepens, the lake forms on top of it. And then we see the arrival of picea or spruce, the dominant boreal forest species today from the beginning of the Holocene. So this was a work that I did with colleagues in Alaska. And one of the things while we were putting this story together, there was a large fire running through part of the Yukon Flats uplands. And this, you can't miss it as long as you aren't color impaired. Ben chose bright pink to show the area of the burn. But what we also see is one of these larger lakes lying in a valley system before and then after the fire. And the lake has partially drained and run out along a drainage system downwards towards the Yukon River. And this happened after the fire. We can see the drainage channel here. And we can also see from Leslie Anderson's photograph that when you burn these rolling loess hills, you get a lot of movement of the loess or silt material in slope wash down slope. Again, giving us the idea that this landscape is very easily triggered into moving. Lakes are triggered into draining. So that is some of the Thor Lakes in Alaska, taking on different forms, different depths. I didn't say, but those lakes in the last illustration were about 10 or 12 meters deep, whereas the ones on the North Slope are more like 2 meters deep. This reflects how deep there is massive ice going down into the ground underneath the surface. And that in turn depends on the nature of the landscape in which the ice wedges have developed. Now, some Thor lakes, particularly these ones that form in deeper loess accumulations, loess coverage of landscapes, were identified by Katie Walter 10 or 15 years ago as methane hotspots. And what happens is that although this material, we call it loess, which we might think is rather organic poor, in fact, these landscapes were Pleistocene landscapes. They were occupied by the so-called steppe tundra vegetation, and mammoth, horse and bison moved across them, and they contain quite labile concentrations of carbon, if only to a few percent. Once we form a lake in the way that we've described, that the ice has melted, the ground's collapsed, we have water, and then we have sediments underneath that. And underneath that, because this is relatively warm, we develop a thaw bulb or an unfrozen area or talik in the underlying materials. All this then can be subject to anaerobic decomposition, there being very little oxygen. And many of the pathways of this decomposition lead to methane. The methane appears and can bubble up through the lakes. So we've got a natural source of methane to the atmosphere, but it's encouraged by Thermokarst. So some of these lakes, great, there's a YouTube here you can watch of Katie setting a match to a hole in the ice during the winter and somebody losing their eyebrows, but it's definitely methane. And here we can see it bubbling up in the clear ice of these lakes out here in the Seward Peninsula. These were the ones we looked at in the Iconos image earlier. And just to mention that one of the things that working with Katie, we identified through radiocarbon dates the trash layers of as many reported Thermokarst lakes from Siberia and Alaska as we could, and showed that their formation in the early Holocene links with increases in atmospheric methane that were occurring in the early Holocene. And to some extent, although this is not numerically balanced, to some extent, the whole thawing out of northern regions that came with the onset of the warm weather, of the warm climate of the Holocene, undoubtedly encouraged a rapid spread of thaw lake formation across these regions and an accompanying boost of methane production. So to move on to Siberia and fire, Thermokarst, people and climate change, we'll go to Sahara Republic here in northeast Siberia. It's a very large area. It has the cold pole of the third pole, if you will, of the planet. A very extreme climate, permafrost underlying it. Traditional lifeways that became resurgent at the end of the period of the Soviet Union. And it's also rich in resources and it's covered in forest. And any maps one looks at for global warming show this part of Siberia subject to very rapid warming, certainly part of polar amplification and part of the warming of the north. Now here's a photograph again of a loess dominated landscape. This is about 45 meters of loess on the Kolyma River. And in it are these very, very large so-called syngenetic ice wedges that basically have kept forming. The ground cracks, water gets in, creates lumps of ice inside the permafrost. And as the loess deposits, then that ice just continues to grow apace. And so these ice wedges can be tens of meters deep, but they tend to have convoluted structures. And the best way to think about this mass of loess and ice is to think about Swiss cheese, but to remember that it's the cheese in the Swiss cheese that is the ice. This is more ice than it is mineral material. It's very typical ice complex of Yakutia. So let us see if we can visit this place. We can, okay.
These are the scars of climate change. Rising temperatures mean that the frozen ground or permafrost is thawing. In this part of Siberia, they're seeing more and more of these. These mounds and hollows are called thermokarsts. Where I'm walking now, this is where the permafrost has been thawing and soil has been sucked down into the earth. You can see some of these hollows have actually filled with water, and a small pond like this can very quickly turn into a big lake. All of this is proof that rising temperatures are changing the Siberian landscape. That means less pasture land and more trouble getting around. Climate change has been causing all kinds of problems here. Where we're driving now was completely flat 20 years ago. There was actually an airport here, and this was the runway. But because the permafrost has been thawing, the ground has fallen away. Siberia even has a whole city built on permafrost. Yakutsk.
Now we stay in 12 meters on the surface.
It has its very own Permafrost Institute, where they measure the rate at which the ground is thawing, because that affects not just the city, but the climate too.
And this is the permafrost, yeah? Yes, it's permafrost. You see this layer, it's enriched organic matter, shrubs, grass.
And what happens when the permafrost thaws?
Organic matter contains a lot of gases, greenhouse gases, and when permafrost thawing, they can go into air.
So the more the permafrost thaws, the more gases go into the atmosphere.
Absolutely right.
Talking of gases, scientists believe that this year's Siberian wildfires have accelerated permafrost thawing as far north as the Arctic Circle, contributing to global warming. But back in Churabcha, it isn't the fate of the planet that's worrying Ilya. He's too busy plugging holes to stop this permafrost pond from becoming a lake and washing away the house he's building.
Изоляция эта доска. Вот и не тает после этого. Не падает, не будет.
All the scrap he can find,
Во всей стране будем.
he's dumping.
Если бы вы это не сделали, что было бы? Она пошла бы как это. Пошла бы даст, и это здесь образовалась бы вода, это озеро.
As for the house, like all the buildings here, stilts are essential.
Говорят же, глобальное потепление этот начинается. Вот если так, не знаю, что будет. Это пускай это дети будет подумает. У меня это уже прошло, наверное.
But what will Siberia be like for Ilya's children if climate change isn't tackled now. At risk are whole communities and livelihoods. As it is, the land here, bizarre, disfigured, is already a permanent reminder that change is happening.
It's kind of hard to follow Steve Rosenberg. I thought he did a very good job on that report from Tarapja. And one of the things that one learns is, can this thaw process be reversed? And Alexander Fedorov and colleagues did some measurements to show that where the trees are regrowing, they can shade the ground and evaporate water and halt this destruction of the permafrost. But the trouble is, there's been much land clearance in these areas, and in many places the trees are not growing back. So this disturbance and this thermokarst continues to occur. The other thing, as was mentioned in that report, is the fires burning through the Siberian forest. And here in this image, we can see where the fires are burning, and here are the smoke plumes. And this is a common occurrence in these forests. And these areas here are the settlement areas where the land has been cleared for animal pastures and the villages where that film was taken. Now, fire then is another disruptor of the surface of the ground. Clearly, if you do clear the forest for an aircraft, for a runway, and disturb it, the likelihood is that you will generate thermokarst. And this is well known, for example, in tundra areas where tracked vehicles are driven across the tundra, and then tracks form, little ponded tracks form, because the same disturbance has caused thaw. And there's been more focus in the last few years about how fire can do the same thing. And so this concern about fire is well taken. In the deposits from the early Holocene in the lakes that have existed for 10,000 years or so in the Yukon Flats area, there was a lot of charcoal. There were clearly fires happening on the landscape. And we saw how fires can lead to lake drainage. And so several papers recently demonstrated, here we see similar ponding and formation of small ponds after a big burn in Alaska. And this study, using ground penetrating radar, has shown how the talik or thawed zone under a fire can be extended from maybe 1 or so to 2 meters deep down to maybe 4 to 6 meters deep. And once you've got that much of the ground thawed, again, it's going to really change the drainage, the nutrition, and possibly lead to ponding, depending on the topographic position of the terrain in this case. So concern about what fires can add to the system. So in the area of the Swiss cheese type ice complex of near Yakutsk, for example, this is what is going on. Now, it has been going on naturally. There have been fires for a long time and other reasons for the land to become disturbed. And lakes have gradually formed through time. And particularly, one can tell from sections in the riverbanks that a lot of lakes have formed quite early in the Holocene. Some of them still exist today, but others are much younger. So we have an ice wedge system under the ground. We have a disturbance that allows ponding and the beginning of pond formation to occur. This then expands into a larger and larger lake with an unfrozen zone underneath it. These kind of mounds that were so prominent in those photographs from Chorapcha are called Bhajaraks, and they're basically the holes of the Swiss cheese. They're basically the mineral material where the ice has melted away and left heaps in the ground. Here we see a current area of the forest quite near Yakutsk where there's been a fire, and again we have incipient formation of a lake. And here we have a nice view of fairly youngish lakes in that area. So one of the things with Alexander Fedorov that my colleagues in Alaska are attempting to do is just find out more about what's been lost. And of course, one of the interesting things is it's actually quite hard to know how big lakes are. You can see cross sections of them when they're cut by rivers, but otherwise you can find out their bathymetry and then estimate their volume, which is what student Max McCann has been doing last year. And so for the area around Chorapcha, we chose the smaller, probably younger tank-like lakes and estimated some volumes, came up with some relationships. And Max estimated that per kilometer squared, really quite a lot of meters squared of ice have been disappearing in Thermokarst thaw. And a very back of the envelope estimation at the moment is also that translates into quite a lot of carbon per kilometer squared. So these lakes are probably young lakes. They're probably formed in probably the last 100 to 200 years, certainly probably in the last millennium. However, it's very often to actually date the progress of lake formation because of a student way back in Alaska with Dave Hopkins once classically described Thor Lakes as the Holocene in a blender, which they are. The sediments all get muddled up as the lake collapses, and it's very hard to get a coherent radiocarbon signal. So one of the things is to try to get more understanding of the dates and the development of these lakes. If we just look at this animation, focus on a village as the animation runs, on a lake, excuse me, as an animation runs, and look at how these lakes are changing in size as the years go by. So there's a series of annual photographs, and we can see extraordinary changes in the shape and size of these lakes. So this adds yet another wrinkle, if we will, another complexity onto what these Thermokarst lakes are doing. They have formed naturally over time. They are forming because of disturbance of the ground by people. They're forming because of fires in the forest, but also they're going up and down. Sometimes they disappear almost completely. And one of the things we have to consider is, although permafrost is largely continuous, the taliks that develop under lakes and indeed under streams may merge. And indeed, as the landscape and the atmosphere warm, there may be gaps forming in the frozen ground that allow water to move around under the surface, tapping a lake, filling a lake, and generally redirecting the flows of water. And this again is shown by GPR and resistivity measurements by these papers from Alaska. And indeed, in Yakutia, the climate moisture balance, precipitation minus evaporation, is also finely balanced. Thus, the climate itself each year can impinge upon the lakes. So this means that water levels and thus usable land areas for grazing stock vary. When the lakes drop down, pollution and water quality issues can become a problem because these are important water resources. And so we have an almost perfect storm of climate variability, the permafrost dynamics changing, the hydrology becoming unpredictable, and disturbance proceeding apace, which lead to major issues for this part of Siberia. So just to summarize this part of the talk, We can think of the Pleistocene landscapes, especially with loess, as respiring on a long-term scale. The landscape builds and incorporates carbon in the glacial periods and then basically breathes it out during warm intervals as thermokarst occurs. And so with a warming of the environment, we're going to expect thermokarst to proceed apace. And then there will be also other changes in the warming climate regime, which are particularly fire, which may again exacerbate the thermokarst, and thus the production of potential feedback via greenhouse gas production into the world's carbon cycle. And we may see a point where the permafrost thaw just gets to the point that you get, again, a catastrophic or non-linear collapse of lakes across whole landscapes, which form a major threat to human activities. So Mark, if I may, I think I've got about 5 or 10 minutes left. I will talk a little bit about the current project that Martin van Hardenbroek and I have called the DEMA project. But I have to start again with Dave, who back in the days of the Cold War, nevertheless wrote letters to all the Soviet scientists that he could find and asked them if they could discuss their shared interest across continental Beringia from Siberia to Alaska. And in particular, he found Andrei Scher, who was a scientist in Moscow, and they had a lifelong collaboration. And there's a very interesting book by Scott Elias and Klaus Dodds, I should say a publication by them, about their persistence in trying to link the scientists of then Soviet Union and the scientists of North America. And this has, I'm pleased to say, propagated down through the generations. So the DEMA project was initiated by contact through my colleague and contemporary Pat Anderson, who was also mentored by Dave Hopkins, and Anatoly Lozhkin, a contemporary of Andrei Scher and also of Dave Hopkins. And between us, we were able to make contacts and bring people together in a workshop about past environmental change in Siberia. And it was very important to have those personal connections. Oh, and I should say the Foreign and Commonwealth Office and its Science Innovation Network was very important in getting this kind of collaboration off the ground. So we had a meeting in Magadan where particularly early career researchers from Russia and a group of 5 of us, ECRs, and Andy Henderson, Martin van Hardenbroek and I came over, and we discussed techniques and some of the software that wasn't perhaps available at that time for people from institutions around Siberia and the Russian Far East, and discussed what we could do. And it was agreed we'd like to develop a longer term collaboration. It was a very successful workshop, and we had other ones that followed that I'll mention in a minute. And we discussed the things that I've just been talking about, the permafrost, the forests, the fire, the response to warming, and the fact that when it comes to any baselines or understanding of how the Thor Lake formation, the forest fires, the changing climates have affected Siberia in the past and up until the present day, there's very, very little information. It's not that there aren't records, there are many records across Siberia, but in terms of answering questions, for example, that current climate modeling and biogeochemical modeling needs to answer, we do not have the right kinds of data yet from all of these sites. It would be wonderful to get more sites. So a sort of joint effort here to gain new material and new understanding about the history and unfolding of these environmental changes is what DEMA would like to do. And it's a good chance for cooperative synergies, because this area is logistically hugely challenging, and the ability to work in it and produce data from it are key strengths. But often the Russian colleagues maybe lack some analytical resources and maybe somewhat constrained in what they can do scientifically, and interaction with international colleagues is a wonderful way of developing a synergy where international colleagues can work with their Russian counterparts in these regions, and the Russian counterparts can work on some new analytical techniques. So this is all good, and a chance to develop research funding. And an aside on the right as to why it took a long time in the pub in Magadan to come up with the developing innovative multi-proxy analyses, but it does spell Dima, and this of course is very famous baby mammoth Dima, which Anatoly Lozhkin discovered in a valley in near Magadan. So to date, the Dima network has had 3 workshops: Magadan, Tomsk, and Southampton. It's developing a special section of Boreas, which is nearing completion, although somehow with COVID, I seem to have said that several times in several talks recently. But I hope it will soon near completion. We've had scientific exchanges. We're working on a joint project. And again, through Henry Burgess's Arctic office and the Science Innovation Network, we've got more small projects approved. We have a National Geographic, a Royal Society project approved, and hopefully some larger projects approved with our Russian colleagues. So just to conclude the whole thing, we've had quite a lot of funding support for the Alaska work, the Yakutia work, and the Dima work. To all those organizations, we're exceedingly grateful. There's a statue in Fairbanks that I didn't even show you a picture of because it's generally considered to be rather awful, of the so-called first family. But in this case, I think Magadan's reindeer first family is thoroughly engaging. So I will leave you with that, and delighted to try and answer any questions. So thank you. Oh. And
Thank you.
I'm back.
Thank you, Mary.
I am back.
Yeah, well, that was great. I'm actually looking for the clapping thing in Zoom. Now, there we go. If you want to, if the audience wants to put their cameras on, it helps kind of having a discussion in a more human way. But it's of course up to you to do so. So well, thanks. Well, we reached the discussion time, and see you, Christian. Christian is saying, Christian Rixen from Switzerland was saying bye. Yep. I have some questions, but if somebody in the audience has one, please go ahead. We are around 20 people, so unless we start kind of running into each other, just feel free to unmute yourself and ask a question if you feel you have one for Mary. Richard, go ahead.
Yeah, you spoke quite a bit about fires, and you indicated that they're sort of increasing at the moment, I guess partly through human activities and partly through changing climate. Have you any idea how they were through the Holocene? I mean, because you have had evidence in the early Holocene, but I guess it's quite hard getting records in the central part of the Holocene.
Yes, you have to have the right lake, so that as you know, Richard, you've got lots of interesting fire records from Scandinavian boreal forest, and there are quite a few from the Alaskan forest derived from lakes. And what is curious is there are very few currently from Siberia, although there are many excellent pollen records from Siberia. Charcoal typically has not been counted that much, although there are some charcoal records. So one of the things that Dima and anybody who wants to join us would like to do is create more fire records from Siberia to exactly find out how fires have happened during the Holocene as climates have changed, which they certainly have. Depending on where you are in Siberia and the Russian Far East, you've got an early Holocene influence of the monsoons and pretty warm but wet conditions, and then that switches to a sort of winter wet westerly system, drier summers in the later part of the Holocene. So I mean, it would be very interesting to know more. And so that's, you know, so hopefully with our Small Royal Society grant, we're going to get some charcoal records from the Irkutsk region, for example. And, you know, anybody who wants to get charcoal records from Siberia, it would be great. There are a few records from that region of Yakutia, from those Thermokarst basins, again, that have charcoal at the bottom and date to the beginning of the Holocene. And many dated trash layers date to that period. But yeah, we don't know at the moment, Richard, and it would be nice to know. And that's one of the things that we'd like to do for sure.
Thanks.
Thanks. I have a question. In the tundra in general, shrubbification and increased size of vegetation is seen as a potential positive feedback for warming, because of reduced albedo and potentially even reduced soil winter temperatures. So somehow this could seem to be a bit at odds with imagining the boreal forest as a protector for permafrost, since, you know, in a way it does the same sort of a function. And in part there is a process that vegetation does in winter, which is keeping the soil warmer by trapping snow and then in summer, which is probably keeping the soil cooler. And I just wanted to ask you, what do you think about this, and how do the two ideas in a way speak to each other?
Yeah, I think that's really interesting, this question of whether the boreal forest with its thick organic layer and mosses and dense cover, and that's more true in the dark taiga, say, you know, of Alaska, than it is in the larynx, the larch taiga. Whether that in a sense is something that particularly in the warm season mitigates against warming of the surface soil, or whether it's keeping the permafrost, you know, warm in the winter, which it also does, you know, which of those plays out. And I think that will be an interesting thing to discuss more. But what seems to have happened, because we've got complete records in Alaska, is that there's a lot of collapse and movement early in the Holocene, at a time actually when it was more like shrub tundra. And then whether they are coincident, but whether they are cause and effect, there is some stabilization apparently as the boreal forest develops across the landscape. And it would be very interesting to simply try and model this, actually, because my intuition is that boreal forest actually does create some kind of sort of inertia in the system. It somehow slowed all that landscape movement, because it just keeps the surface, you know, completely anchored down. As to the greening of the tundra and the shrubbification of the tundra, depending on what it is, and if there's a lot of Betula nana or Betula glandulosa, I mean, one thing is that burns, and there are noticeable tundra fires. I mean, as you know, which then get us back to that sort of disruption of the surface and possible, instigation of thaw. So as always, these things are somewhat finely balanced, and you can follow two pathways, and which one it will go in would take some doing some sums, I think, probably. But it may also vary depending on so many factors. But I'm not. The shrubbification, I mean, there's also this interest in the fact that shrubs do in one way, you know, consume more carbon dioxide and thus possibly act in as a negative feedback to warming. But in another case, as you say, the soils may actually be activated by this and thus form positive feedback to warming. So another finely balanced area. Yeah.
Thanks. Is there any question or follow-up comment on this? Andrew Wells has raised a hand. Please, Andrew, go ahead.
So firstly, thanks for a fascinating talk. Some of the mechanisms you were describing about some of the mergers of these lakes and the melting that was going on also underneath the ground reminds me a little bit of some pattern formation problems you get in freezing and melting systems in sea ice. So I was wondering, has anybody looked at this as a dynamical pattern formation problem as a physical system before?
Ooh, well, Lawrence Plug did an interesting study which looked at sort of working up to this, that looked at why do ice wedges form the patterns they do at a landscape scale, and did the thermodynamics and did calculate why they form where they do. And he was also involved in some modeling of the Thor Lakes themselves, in terms of the way that one would expect them to initiate and expand. But I'm not sure either of those addresses what you were saying about sea ice patterns, does it? Maybe you can explain a bit more.
You kind of, in sea ice, you kind of get patterns where you get localized patches of melting where there's some feedback. So I guess here it would be the slumping of or the compaction of the ground as you start to remove the frozen ice from the system and change to liquid water would be the relevant feedback. But you can kind of get pattern formation and mergers between adjacent channels or lakes of enhanced melting.
Oh, I think you do get that. So one thing is that it's very likely that the increased moisture that came at the end of the glacial period was as important as the warming temperatures for initiating widespread thermokarst, which is what seems to have happened across Siberia and Alaska, because if you get more surface water ponding up, for example, in the spring in low points or impeded drainage, that'll get your melting started, like maybe on sea ice. So that there would be, you know, it'd be slightly predictable where you might see this happening. And the other thing is at the landscape scale, at the scale of the way the ice wedges run underneath the surface, those lakes I showed from the uplands clearly anastomose and run into each other because they're quite odd shapes, and you can see that they've sort of joined together as well. So so the lakes build by gradual thermo erosion, but then sometimes they'll run together and form kind of a, you know, dumbbell lake or a blobby lake or something like that. So they are anastomosing like that as well.
Talking about lakes and lake shapes, we have had some difficulties in choosing which lake to core in places such as Yamal, which are on continuous permafrost, where lakes are nicely lenticular many times, and you never know if they're going to be extremely young or we're going to hit the jackpot and have a record for the Holocene, for example. Is there any hint or you know, some sort of a trick to basically go for the old ones by looking at their shape?
It's a great question, because I've thought about that a lot. So it's very interesting if you poke around enough and do some radiocarbon dating and look at sections and things like that in the Seward Peninsula. And this is I'm now channeling Dave Hopkins, because he began any explanation of anything in the Seward Peninsula. But the sites that I showed near the beginning, where the lakes had drained and kind of cut into each other, it looks as if lakes are not that long lived in any situation where there's slopes and potential for tapping and river valleys, lakes tend to be quite young, and we cored a lot of those lakes, and they were either quite young or they were the Holocene in a blender, and very few of them were old. And I remember Herb Wright and Dave Hopkins standing looking at this lake, and Herb going, "Oh, it looks deep to me. Surely that would be good to core." And Dave's going, "Herb, it's not," because it is, you can't tell. And in the Yukon Flats, most of the lakes have coherent sequences and they're old. And I think it's because the climate has been such that they have not come up and overflowed and cut down and by and large emptied. They've stayed in their basins, and a lot of them now have dropped in their basins quite considerably. They're still there, but clearly, you know, they've dropped down, and it's some combination of fairly stable underground water systems, deep holes in the ground because it's a deep-less system, and P being usually a bit less than E, so that they don't really fill. But if they fill and overflow, they don't last very long. It doesn't really answer your question about Yamal, because Yamal's got these weird round lakes, and they are probably Thermokarst lakes. And I wouldn't know, to come back to, I wouldn't know how to tell which one's wrong. I mean, we always look for lakes that don't look like Thor Lakes, which means that maybe there's evidence they've been a landslide has dammed them, or in some kind of high ground, but they're not on a flat plain. Have you found any, Mark? Have you found any that have good records?
No, well, no. There was a couple, of course, extracted from Yamal in a previous project some years ago, and they had very weird dating. I mean, yeah. the radiocarbon dates were in one case very short, and the other very confusing. So yeah, no luck yet. That's the problem, right? That you cannot just have 100 and see which one works. So
yeah. I think Viv Jones was trying in the northwestern lowlands and had the same issues with them. Because they're mostly Thor Lakes, but they're not all Thor Lakes. But it's hard to find the ones that aren't.
Okay, well, disappointing. I just wanted the 5 golden rules. Rachel has had her hand risen for a while, so go ahead, please.
Sorry, I don't know how to put it back down. But yeah, thanks for the talk. That's been really interesting. It's a bit of a vague one, but I was really interested in what you mentioned about, I think you mentioned a few aspects of that sort of interaction between fire and Thermokarst. And I was just wondering if you could say a bit more about sort of maybe what you see as the kind of the dominant sort of aspects of that interaction. I was just thinking, like, is that something that you see as sort of accelerating that sort of full progression of Thermokarst development, or is it something that is more kind of initiates ponding, and you know, how sort of transient or otherwise do you see that relationship being? Just be interesting to hear a bit more.
I think that's really interesting, and it's going to depend on where the fire was, what the ice under the ground is like where that fire was, probably the following on conditions as to whether the ground recovers its vegetation quickly or doesn't. I do think that this increased concern is, I mean, it's partly because we've got enough remote sensing records now to see that the landscape is changing, to look at fire scars and to look at lake formation and to see whether there is some kind of linkage between them. And I think it is all speeding up. And that's why people are writing papers in prominent journals about how fires seem to be affecting Thermokarst. It's the low-lying areas in Alaska where this is happening. I mean, when you're on a slope, it's a little different because you've got water drainage and you need that ponding. So it's the flat low-lying areas, or the sort of flat uplands of that Yakutian. They're river terraces, and they're pretty flat. You know, each one's covered in loess and is fairly flat. And those are kinds of places where you can get the fire happening. The ground color changes. The moss layer is perhaps partly burned off. Radiation, etc.
Thank you.
Yeah, and then the talik, you know, it's quite interesting. Then it thaws way down, and then if you've got ice there, then you've got a hole in the ground. If it's not particularly icy, then maybe the forest grows back and nothing happens.
Great. Rachel, you have your hand up. Is this because you want to continue the discussion?
No, I just don't know how to.
Okay, we call them legacy hands. So, all right. Any new hands? No, no questions about Dima or the kind of the other side of or the other talk, the sub talk or post talk of Mary. There was I mean, just a comment about Dima, not about Dima, but one of the slides you showed, of course. It's good to highlight how little data we have from Siberia, but at times it's very much the result of English-speaking researchers not really being able to really find the literature, and which calls for further cooperation, right? But I had a question about that, and it is how much of what's missing, because you were saying. Certain data for example, our system models needs to be of a given in a given way. How much of what's missing is our lack of you know, accessibility to Russian literature, and how much of what's missing is missing?
This is a really good point, and I did try to say, and you did pick it up, so I was at least partly successful. It's not that there aren't records across Russia, and a lot of work has been done. And you're right, we don't know about it because it's in the Russian literature. When we want, for example, a coherent set of radiocarbon dates, quite well spaced in a core to be able to create an age model, for example, those are often lacking. One of our colleagues in Tomsk has a collection, for example, for the Western Siberian plain of about 100 pollen diagrams carried out by Russian researchers, but they have maybe one radiocarbon date. So they are not what we can use necessarily for reconstructed proxy chronologies that allow, you know, whatever, model evaluation or sort of, you know, other things like climate, you know, reconstructions through time. This is the problem. A lot of work and a lot of very good palynology, but no dates, for example. And when we look at what's been done in Siberia, more recently, there are lots of good records. You know, with lots, there are new records with AMS dates now, and that's really good. And a lot of them have been international collaborations, which is fantastic. So for Dima, it will be absolutely important to do what one can with the sort of legacy of Russian records. So if, for example, you want to know how much peat there is across Western Siberian plain and roughly how old it is, then you've probably got 100 records that can help you figure that out. But they're not going to give you a chronology of, you know, of peatland development, for example. That's the problem.
Thanks. Great. All right. Any other questions or comments or suggestions? No? Okay, well then, yeah, we can thank Mary again for both the talk and the discussion. And I thank you all for coming, and stay tuned for more seminars that will come in the near future on this spring seminar series of the Oxford University Polar Forum. And that's it. Just to remind you that we have been recording this and we have a YouTube channel, so it will be uploaded there sooner than later, so that you can revisit things if you, for example, didn't write down a given reference or something. It's going to be there and available publicly. All right.
And the DEMA website is there. And if anybody is interested, please contact me or Martin because we really welcome new researchers to the group.
Yeah, thanks for highlighting that.
Yeah.
Great. Okay, well, thanks, Mary. Thanks a lot.
Oh, you're welcome. Thank you. Thanks, everyone. Nice to see you.
Goodbye.
Bye-bye.